few months ago, I spoke with Andrew Zonenberg about characterizing the RAM produced by OpenRAM. That's the same RAM that we're using in the Caravelle harness on MPW1, 2, 3, and so forth. Components have arrived and the PCBs have been ordered, so we thought it was time for another update. And if you've not seen the first episode, then you can click on the link above and check that out. So how have you been doing anyway?
Crazy as you would expect from dealing with a new baby in the middle of a pandemic.
Yeah.
But we're making things work.
Good. So I guess we can just jump straight into ask you if you could give us an update on where you've got up to.
All right, perfect. Yeah, let me put up the... Okay, so here is the first board that has been designed for the project. This I'm calling the brain, for lack of a better term. It's the controller for all the testing. Block diagram-wise, we've got power regulation over here, then a STM32 F0 and an Arctic 7 FPGA. And the microcontroller also has access to a DAC, which controls I believe it's a power op amp. Actually, it's basically being used as a linear regulator to produce a variable core power supply for the device under test. The idea being we want to test things like RAM retention at lower voltages and see how low can we actually go. It's nominally 1.8, but okay, do we lose data at 1.7? Do we lose data at 1.6? How far can we actually push it? And then there's some current monitoring and stuff like that as well. The I/O is always running at 3.3 for this test. And as you can see, the traces are fairly tightly length matched. This is certainly overkill for functionality at these speeds, but I'm hoping to be able to do things like measuring setup and hold times of the memory. And so in order to do that, I don't want to have too much skew introduced by the board. These are actually not matched to equal length. They are matched to compensate for the routing skew on the breakout board, which I will show next.
So that's the base board that's always going to stay the same, and then we'll be able to put other types of boards on top.
Correct. And so for now, the only one we've got is for the OpenRAM test chip, which I'm going to... Okay, and so here is the other one. So we've got the test chip, we've got a few test points for the core and I/O power, and then the connector on the backside with some decoupling caps. It's pretty straightforward. Again, the trace links are tuned so that the longest ones here match with the shortest ones in the other board, and vice versa. It was easier than trying to get them all exactly the same length in both boards. And the maximum skew I calculated, I think it's around plus or minus 60 picoseconds from the clock for each signal, and that's tight enough that it shouldn't matter for the speeds of the I/O. The slew rate of the I/O buffers is going to limit the measurement accuracy, I think, more than the skew on the board at this point. But I wanted to kind of future-proof a little bit for maybe if we get a next generation chip that's got faster I/O buffers on it or something, I wanted to at least have the possibility.
So how badly were you impacted by the supply chain shortages?
That has actually really annoyed me because I had the FPGA in my DigiKey cart as I started designing the board. It was in stock, and by the time I clicked buy, it was gone. And so that little delay ended up costing us about 2 months. Then there was an additional delay of about another month unrelated to the shortage just because we were busy dealing with baby stuff and things were getting pretty hectic, and I only got back to the board design pretty recently. But that is all at least mostly under control at this point. The boards have been ordered. Oshpark is fabbing them pro bono, and I'm donating components. So the components are here. I believe we've got all the parts. The boards are expected to be here in about 2-ish weeks. The stencil was also ordered, and I'm waiting on that. It should only be a couple of days, so I expect it to outrun the boards. And so with any luck, by probably end of this month-ish, I should have the host board and the 3 breakouts with 3 of the test chips. I believe I do have more than 3 test chips, but only putting 3 of my boards to start. So I'm going to have the host board and the 3 test boards with 3 different dies, all soldered up and ready to start writing firmware and gateware for.
That was my next question, was where are you at with the firmware and the gateware?
Non-existent right now. So the high level structure is going to be the STM32 is going to do kind of the state machine sequencing and control report overall results, and then communicate over, I believe, a SPI bus to the FPGA, which is going to do all of the individual read and write transactions. And so it shouldn't be that complicated. I actually was just writing some FPGA memory test code for an unrelated project. And so it would surprise me if I can reuse a bunch of that code for this. But yeah, it's pretty straightforward. I'm probably just going to fill all the memory with a PRBS31, read it back, fill it with the complement of that, and read it back. And then repeat that, sweep it at a bunch of different timings, a bunch of different core voltages, test things like, again, data retention across voltage ranges. I am working on possibly getting access to some sort of environmental chamber in order to test performance across temperature, so we can see if the memory is hotter or colder. Does it use less power? Does it run faster? Does it lose bits at more or less voltage, etc.?
What's PRBS31?
Pseudo-random bit sequence. It's a linear feedback shift register. There's a bunch of standard ones that have, in this case, it's 2 to the 31 minus 1, I believe, is the period of it. So it's a 31-bit state, and the all-zero state is illegal because that would never get anywhere, because XORing 0 with itself, however you shift, isn't going to get anywhere. So you got to have at least 1 bit in the register.
Okay.
And so yeah, there's a bunch of just standard maximal length LFSRs used for generating pseudo-random but predictable data for testing serial links in memory and stuff like that. And so I already have, okay, it's like 3 lines of code, but I've already got a PRBS31 FPGA block, so I'm just going to go throw it down here and call it good.
Cool. So what would you predict the timeline to be for getting some results out of your test setup then? A couple of months?
Yeah, it shouldn't be that time consuming. I mean, some of the more advanced testing, like testing byte write enables and stuff like that, is going to take a little bit more work. But for the initial just functional test with just writing whole bytes and reading them back and not doing any weird things with sweeping supply voltages, and again, just have it all running at nominal voltage and just verify functionality of one die. Honestly, that should only take a couple of days to write up. It's just a question of when I'll be able to find enough time when I don't have a crying baby on my lap to do it.
When's your baby going to start helping you write gateware? That's what we want to know.
Yeah, that's a good question. You probably saw the picture I tweeted a while ago holding up the Dunsmore. And she was a lot more interested in her little turtle friend dangling from the rocker, so...
Maybe a few more years.
Yeah, we'll give it a little while.
Great. Well, I think that's probably it for this update.
Boards are ordered, and I could start writing firmware while I'm waiting for them to come back, but I've got enough stuff on my plate, I probably won't have time, so I'll wait until the hardware is here and do some functional testing. And
you don't want to break the golden rule of developing firmware and gateware too early either, do you, really?
Yeah, well, we'll see how it goes.
Great. Okay, well, thanks a lot for your time again, Andrew, and looking forward to the next update.
Okay, you too.